There is something quietly extraordinary about the fact that you are lying here right now, breathing slowly, while beneath everything you can see or touch, the universe is doing something deeply, beautifully strange. Welcome to Sleepy Science, where tonight we're going to drift together through the quantum world, the smallest, softest, most wonderfully peculiar layer of reality. If you enjoy these quiet journeys, please consider leaving a like, subscribing, and letting us know in the comments what topic you'd love to fall asleep to next. And if you'd like to help keep these videos going, you can find the Sleepy Science Patreon quietly waiting for you in the description. Now, let's go somewhere very, very small. Everything you have ever touched in your entire life has been made of atoms. The blanket over you right now, the pillow beneath your head, the air moving softly in and out of your lungs. All of it, every last thread and molecule, is built from these tiny, ancient, almost impossibly small things. And yet, for most of human history, no one knew atoms existed at all. People looked at the world, at rivers and rocks and the light of the sun, and they saw surfaces. They saw the world as it appeared to them. They had no way of knowing that below the visible, below the touchable, there was an entire other world, operating by rules so strange that even the scientists who discovered them were not entirely sure what they meant. The atom itself is mostly empty space. This is one of those facts that sounds simple when you first hear it, but then, if you sit with it for a moment, it begins to do something unusual to you. If you could somehow take all the empty space out of every atom, in every human being on Earth, all 8 billion of us, the actual physical matter, the stuff, the substance, would fit inside something roughly the size of a sugar cube. A single sugar cube. 8 billion people, compressed into something you could hold between 2 fingers. The rest, all the rest, is space. And inside that atom, at the very center, there is a nucleus. The nucleus holds almost all of the atom's mass, in an almost impossibly small space. Around it, in what we often picture as orbits, are electrons. But here is where things begin to soften, at the edges, and become something harder to hold in the mind. Electrons are not like little planets, circling a small sun. They are not objects sitting in fixed places. They are, in a sense, smeared out across a region of space, existing as a kind of cloud of possibility, a probability, a breadth of potential location, rather than a dot sitting precisely, here or there. This is one of the central strangnesses of quantum physics. At the scale of very small things, atoms, electrons, particles smaller still, nature does not behave the way you might expect. Things do not have definite positions until something interacts with them, until something looks. Before that moment, a particle exists as a superposition, a gentle, simultaneous blur of many possible states at once. It is perhaps the quietest revolution in the history of human thinking. The discovery that at the deepest level of the world, reality is not fixed. It shimmers. The word superposition sounds technical, and it is, but the idea it points to is almost dreamlike. Imagine you placed a coin on a table. In the everyday world, that coin is either heads or tails. You don't have to look at it. It already is one or the other. But in the quantum world, a particle like an electron can be, genuinely, in a sense that is not merely a matter of our ignorance, both states at once, until the moment it is observed. Not just unknown to us, but actually, in a deep physical sense, undecided. The universe itself, at that level, holds the question open. This idea troubled a great many brilliant people when it was first proposed in the early 20th century. Scientists who had spent their lives believing that nature was precise, deterministic, like a vast and perfect clock, ticking away, found themselves confronted with something they could not quite accept. One of the most famous expressions of this discomfort came from a physicist named Albert Einstein, who spent much of his later life arguing that quantum theory, however useful, must be incomplete. He felt deeply that the universe did not, could not, play dice. He was wrong, as it happens. Or at least, the experiments since have said he was wrong. But there is something almost tender about a brilliant man refusing to believe that the world he loved studying could be so fundamentally strange. There is a thought experiment that has become one of the most quietly famous ideas in all of science. It involves a cat. A physicist named Erwin Schrödinger imagined a sealed box containing a cat and a small device connected to a radioactive atom. If the atom decays, a random quantum event, the device triggers and the cat does not survive. If the atom does not decay, the cat is fine. Now, while the box is sealed, the atom is in a superposition. It has both decayed and not decayed. So what about the cat? According to a strict reading of quantum theory, the cat is simultaneously alive and not alive until you open the box and look. Schrödinger did not mean this as a beautiful idea. He meant it as a kind of gentle complaint, a way of showing how strange quantum theory becomes when you try to apply it to the everyday world. But the image stayed. It endured, because there is something in it that the human mind recognizes, even without fully understanding it. The act of observation in quantum physics is not passive. When we measure a particle, when we interact with it in a way that yields information about its state, the superposition collapses. The quantum fog condenses into a single definite outcome. The coin lands. But here, and this is the part worth lingering on, the outcome is not determined by anything hidden, anything predictable, anything we simply haven't measured yet. It is, as far as anyone can tell, genuinely random. We can say with great precision what the probability of each outcome is. We cannot say, ever, which one will actually happen. The universe keeps that secret, all the way down. Now, let us move gently to something called the wave-particle duality. For a very long time, scientists argued about whether light was a wave or a particle. Some experiments seemed to show it was a wave. It spread out. It interfered with itself. It bent around corners in a soft and liquid way. Other experiments seemed to show it was a particle. It struck things like a tiny thrown stone, arriving all at once, in a definite location. The answer, when it finally came, was both and neither. Light behaves as a wave, when no one is looking for it to be a particle, and as a particle, when you look for it as one. The question you ask shapes the answer you receive. This extends to matter as well. An electron, a tiny piece of matter, something with mass, something you might imagine as a miniature ball, also behaves as a wave. When electrons are fired one at a time, at a barrier with two narrow gaps, something quietly remarkable happens. Each electron passes through and lands on a screen beyond. Over time, as more and more electrons arrive, a pattern emerges. Alternating bands of many and few, the fingerprint of waves interfering with each other. But each electron was fired individually. Each one traveled alone. How did it interfere with itself? The answer, unsettling and beautiful in equal measure, is that each electron traveled as a wave of probability, through both gaps simultaneously, interfering with its own possible paths, and only became a particle, only became a point, when it struck the screen and was observed. If you then place a detector at the gaps, to see which one the electron goes through, the interference pattern disappears. The act of watching changes what happens. The electrons now behave like particles, going through one gap or the other, landing in two rough clusters. No wave, no interference. It is as if the universe knows when it is being watched and behaves accordingly. Of course, the universe does not know anything, but the effect is real. It has been measured thousands of times. Observation changes things at the quantum level. The world responds to attention in ways that have no parallel in the ordinary world above. There is a quantity in quantum physics called Planck's constant. It is named after a physicist called Max Planck, who discovered it at the very beginning of the 20th century, while trying to solve a problem about the light emitted by hot objects. Planck's constant is extraordinarily small, a number so tiny that writing it out would fill this sentence with zeros and still feel insufficient. But it is not zero, and its tininess is what makes the quantum world invisible to us in ordinary life. The quantum strangeness, the superpositions, the interferences, the waves of probability. All of this gets averaged out, washed away, smoothed into classical predictability, at the scale of things we can see and touch. The quantum world is always there, beneath everything, humming away in its strange fashion. But to us, it is mostly silent. Planck proposed something that seemed, at the time, more like a mathematical trick than a physical truth. He suggested that energy is not continuous, that it does not flow smoothly, like water, in any amount you like. Instead, energy comes in discrete little packets, tiny, indivisible chunks. He called them quanta. This was a strange idea. It went against everything physics had assumed. But it worked. It explained the data. And in explaining the data, it cracked open a door that would take the rest of the century to walk through. The photon is the quantum of light. It is the smallest possible package of electromagnetic energy, the irreducible unit, the minimum. When a light bulb glows, it is releasing a torrent of photons, billions upon billions of them every second, each one a tiny parcel of energy, traveling at the same speed, the fastest speed possible. And yet each photon is, in itself, a quantum object, subject to all the strange rules of the quantum world. A single photon can be polarized in two directions at once until measured. It can take multiple paths simultaneously until something forces a choice. Light, the very thing you use to see, the thing that warms you, the thing that has made the world visible to living eyes for billions of years, is, at its most fundamental, a strange and undecided thing. Let us settle for a moment into something called the uncertainty principle. It was formulated by Werner Heisenberg, a young physicist in the 1920s, and it is perhaps the most quietly profound statement that physics has ever made. It says, in its simplest form, that you cannot know both the exact position of a particle and its exact momentum at the same time. The more precisely you pin down where something is, the less you can know how fast it is moving or in what direction. And the more precisely you know its momentum, the more its position dissolves into a soft blur of possibility. This is not a limitation of our instruments. It is not a failure of technology, something we might one day overcome with better tools. It is a fundamental feature of reality. The universe will not let you know both things at once. It holds something back, always. There is something almost restful in this, if you let yourself feel it. Even the universe keeps some things uncertain. Even at the deepest level, there are things that are simply not pinned down. Nature permits itself a kind of softness, a deliberate imprecision, a refusal to be fully known. You are lying here, breathing, and the electrons in your body are dancing in this gentle uncertainty, never quite here, never quite there, smeared through their probability clouds, like a soft watercolor wash that never quite dries. The uncertainty principle also applies to energy and time. Over a very short interval of time, the universe allows energy to fluctuate, to briefly borrow, in a sense, a little more than it ought to have. And this leads to something that sounds almost like a fairy tale, even in empty space. in a region from which every particle has been removed, the most perfect vacuum that can be created. The uncertainty principle means that pairs of particles can briefly pop into existence, out of nothing, exist for an instant, and then annihilate each other and vanish. These are called virtual particles, and the empty space of the universe is seething with them, an invisible, constant, silent fizzing at every point in space. The void is not empty. The void has never been empty. This vacuum energy has real effects. One of them, measured in labs, is called the Casimir effect. If you place two very thin metal plates extremely close together in a vacuum, close enough that the wavelengths of many virtual particles are too large to fit between the plates, then fewer virtual particles appear there than on the outsides of the plates. The pressure from outside is greater than the pressure from between, and so the plates are pushed together by nothing, by empty space, by the quantum breath of the vacuum. It has been measured. It is real. Empty space pushes things. Now let us drift toward something called quantum tunneling. Imagine a ball rolling toward a hill. In the ordinary world, if the ball does not have enough energy to reach the top of the hill, it rolls back. It cannot pass through the hill. It does not have the energy. But in the quantum world, a particle, like an electron, that approaches a barrier it should not have enough energy to cross, can, sometimes, simply appear on the other side. It has tunneled through, not over, the barrier. Not because it found a gap, not because it borrowed energy from somewhere, but because its wave function, its cloud of probability, extends a little way into and through the barrier. And there is a small but real chance that when the particle is observed, it is found on the far side. This is not a theoretical curiosity. Quantum tunneling is happening right now, inside you. The chemical reactions that sustain your life, the enzyme reactions, the electron transfers, the processes by which your cells make energy, depend, in part, on quantum tunneling. The sun, the source of almost all the energy in the world, shines because of quantum tunneling. Deep in the sun's core, hydrogen nuclei must approach each other, closely enough to fuse. But they are positively charged, and like charges repel each other. The temperature at the sun's core, vast as it is not quite hot enough to force nuclei over this repulsive barrier by ordinary means. But they tunnel through it. The sun burns because particles can pass through barriers they have no right to pass through. The warmth on your face on a summer afternoon is the warmth of quantum tunneling. Tunneling is also the principle behind the scanning tunneling microscope, one of the most quietly extraordinary instruments ever built by human hands. It uses a metal tip brought so close to a surface that electrons tunnel across the gap between them, producing a current. By mapping how this current changes as the tip moves across the surface, scientists can produce images of individual atoms. Not diagrams, not representations, but actual images, actual pictures of single atoms arranged on a surface. You can see the bumps where each atom sits. You can count them. The invisible made visible by teaching machines to feel the quantum breath between things. Let us rest here for a moment and turn toward something that may be the strangest idea in all of quantum physics. It is called entanglement, and it is the one that even physicists who have spent their lives thinking about these things sometimes say they find quietly unsettling. At 3 a.m, entanglement happens when two particles interact in such a way that their quantum states become linked. Not merely correlated, not like two gloves from the same pair, where finding the left glove tells you the right glove is somewhere too, but genuinely, deeply, in a way that has no classical equivalent, connected. When you measure one particle of an entangled pair, and it collapses into a definite state, the other particle, wherever it is, however far away, instantly collapses into the corresponding state. Not after a delay, not with time for a signal to travel. Instantly. Einstein called this spooky action at a distance. He meant it as a criticism. He thought it showed that quantum theory must be wrong or incomplete, that there must be hidden information traveling between the particles that accounted for the correlation. But experiments have shown, definitively, over decades of careful work, that there are no hidden variables. There is no secret signal traveling between the particles. The correlation is real. The connection is real. Two particles, created together, then separated by any distance, a meter, a kilometer, the width of a galaxy, remain linked in their quantum states in a way that nothing we call classical can explain. This does not allow faster-than-light communication. That door remains closed. The measurement outcome is still random. You cannot control what result you get, so you cannot send a message. But the correlation itself, the spooky action, the quiet thread between particles, stretched across space, is real. There is something deeply human about finding this disturbing. We are creatures of place. We experience ourselves as here, located, bounded, our influence fading with distance, the way warmth fades from a cup of tea. And yet the universe, at its smallest level, does not seem to care about distance in the way we do. Two particles that have met remain somehow connected, as if space is not the separator we imagined it to be, as if the distance between things is, at some level, not entirely real. Entanglement is not just a curiosity. It is the engine behind a new kind of technology that is still in its early days, but growing quietly. Quantum cryptography uses entangled particles to create encryption keys that cannot be intercepted without being disturbed. Because any attempt to measure a quantum system changes it, and the change is detectable. Quantum computers, which exist in small and imperfect forms today, use the superposition and entanglement of quantum bits to perform certain kinds of calculations that would take ordinary computers longer than the age of the universe. The quantum world is not only strange, it is useful, and we are only just beginning to learn how to speak its language. Let us move now to something called spin. In quantum physics, particles have a property called spin, that is, in some ways, like angular momentum, like the way a top spins or the Earth rotates on its axis. But only in some ways. Quantum spin is something deeper and stranger, a fundamental intrinsic property, not a rotation in ordinary space. You cannot make an electron spin faster or slower. Spin is simply a thing electrons have, like mass or charge. And it has only two possible values, when measured along any given direction, up or down. The strange part is that before measurement, an electron's spin is in a superposition of both, and the direction you choose to measure it in affects what you find. There is no single fact about an electron's spin waiting to be discovered. The question you ask and the direction you ask it in shape the answer. Electrons also have a property that gives them a tiny magnetic moment. They act in a gentle way like tiny magnets. This is because of their charge and their spin. And the behavior of these tiny magnetic moments, when placed in a magnetic field, is the basis for something you may have encountered. In medicine, magnetic resonance imaging. MRI scanners work by aligning the spins of hydrogen nuclei in your body, using a powerful magnetic field, then disturbing them with radio waves, and listening to how they settle back. The signal they emit, as they relax back into alignment, tells the machine where the hydrogen is, and therefore where the soft tissue is, and therefore what your body's interior looks like, without a single cut. The deep strangeness of quantum spin made medical imaging possible. Your body has been mapped by quantum mechanics. There is a rule in quantum physics called the Pauli exclusion principle. It was proposed by Wolfgang Pauli, a physicist of the early 20th century, known for being extremely demanding of other people's work, including, famously, his own. The principle says that no two identical particles of a certain type, called fermions, which includes electrons, can occupy the same quantum state at the same time. Two electrons in the same atom cannot have exactly the same set of quantum numbers. They must differ in at least one way. This sounds technical, and it is, but what it means in practice is something quite profound. It means that matter takes up space. It means that your hand does not pass through the table. Without the Pauli exclusion principle, electrons could all crowd into the lowest energy state, and atoms would collapse. Matter as we know it, solid, durable, substantial, exists because of this quantum rule. The solidity of the world is a quantum effect. Let us think for a moment about the periodic table, that quiet grid of elements that chemistry teachers hang on the wall. Hydrogen, helium, lithium, carbon, oxygen, the building blocks from which everything is made. The reason there are different elements at all, the reason hydrogen is different from helium, and carbon is different from iron, is quantum mechanics. Each element has a different number of protons in its nucleus, and those protons determine how many electrons the atom holds. And the quantum rules, the allowed energy levels, the Pauli exclusion principle, the way electrons arrange themselves in shells, determine how each element behaves, what it bonds with, what it looks like, whether it is a gas or a metal, whether it glows or rusts or burns. Chemistry is quantum mechanics, dressed in a white coat. Every smell, every flavor, every color you have ever perceived is the result of quantum-level interactions between electrons. The color of things is worth dwelling on. When light strikes an object, some wavelengths are absorbed and some are reflected. The wavelengths that are reflected reach your eye, and your eye's cells respond to them, and you perceive a color. But the absorption of light happens at the quantum level. Electrons in the atoms of the object absorb photons only if those photons have exactly the right energy to bump the electron from one energy level to a higher one. Each transition requires a precise energy, a specific quantum. If the photon's energy does not match, the electron ignores it. So the color of a rose is determined by the precise quantum energy levels of the electrons in its petals. The red of blood, the blue of the sky, the gold of autumn leaves, all of it painted by quantum jumps. Let us now move towards something called quantum field theory, which is the deepest framework physicists have found so far for describing how the world works. In quantum field theory, the fundamental entities are not particles. Exactly. They are fields. Imagine a vast, invisible ocean, spread across all of space. Not one ocean, but many, one for each type of particle. There is an electron field, spread everywhere. There is a photon field, a quark field, a Higgs field. These fields permeate the entirety of space, from here to the edge of the observable universe, and presumably beyond. Particles are not little balls floating in these fields. Particles are disturbances in the fields, ripples, excitations, places where the field is doing something more intense than usual. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. Everything that exists is a vibration in the deep fabric of things. This idea that particles are excitations of fields means that particles can be created and destroyed. When an electron and its antimatter partner, a positron, meet and annihilate each other, they do not disappear into nothing. Their energy ripples into the electromagnetic field, creating photons. The disturbance in the electron field quiets. The disturbance in the photon field grows. And when photons of sufficient energy pass through space, they can spontaneously produce an electron and a positron, matter and antimatter emerging from a ripple of energy. Energy and matter are interchangeable in the quantum field. One becomes the other under the right conditions. Antimatter. Every type of particle has an antimatter counterpart, a twin with the same mass, but opposite charge, and other reversed quantum numbers. The electron's twin is the positron. The proton's twin is the antiproton. When matter and antimatter meet, they annihilate each other completely, converting entirely to energy. This is the most energy-dense reaction the universe allows. It is, in principle, the ultimate fuel. Nothing left behind, no ash, no waste. Just pure energy, blooming outward. The quiet question that this raises is one of the great mysteries of modern physics. When the universe began, matter and antimatter should have been created in equal amounts, and then they should have annihilated each other completely. There should be nothing left. No atoms, no stars, no you. And yet, here you are. Something tipped the balance. Some tiny asymmetry in the early universe. Some very slight preference for matter over antimatter. And everything that exists is the thin residue of that asymmetry. You are a remnant, a survivor. Everything is. The standard model of particle physics is the framework that describes all the known particles and how they interact. It is one of the most successful theories in the history of science, tested to extraordinary precision, and always, so far, confirmed. In the standard model, matter is made of fermions, quarks and leptons, and forces are carried by bosons. Quarks come together to form protons and neutrons. Leptons include the electron and its heavier cousins, the muon and the tauon, as well as the ghostly neutrinos. Bosons carry the forces. The photon carries electromagnetism. The gluon carries the strong nuclear force. The W and Z bosons carry the weak nuclear force. And the Higgs boson, detected in the early 21st century, after decades of searching, is associated with the Higgs field, which gives mass to certain particles. Without the Higgs field, particles like the electron would have no mass at all. They would travel at the speed of light. Atoms could not form. Chemistry could not happen. Life could not exist. The Higgs field permeates all of space, and it is, in a sense, the thing that lets things be things. Let us think about quarks for a moment. Quarks are the components of protons and neutrons. They come in 6 varieties, called flavors: up, down, charm, strange, top, and bottom. These names are whimsical and deliberately unserious. Physicists naming things in the middle of the 20th century with a certain lightness. A proton is made of 2 up quarks and 1 down quark. A neutron is 2 down quarks and 1 up quark. Quarks are held together by gluons, the carriers of the strong nuclear force. And the strong nuclear force is, as its name quietly suggests, very strong, the strongest of the fundamental forces. But it has a peculiar quality. Unlike gravity or electromagnetism, which weaken with distance, the strong force behaves like a rubber band. The further apart two quarks try to move, the stronger the force pulling them back. If you try to pull two quarks apart far enough, the energy you put in is enough to create new quarks. So instead of separating, the bond breaks by producing a new pair. Quarks are never found alone. They are always confined together, always in groups, always bound by the gluon's invisible threads. The neutrino is perhaps the most ghost-like of all particles. It has a tiny mass, very nearly zero, though not quite, and it interacts with almost nothing. At this moment, a torrent of neutrinos is passing through you. Every second, many hundreds of billions of them stream through every square centimeter of your body, as if you were not there at all. Most of them come from the sun. They were produced in the nuclear reactions, deep in the sun's core, and they travel outward at almost the speed of light, and they pass through the Earth, as easily as light passes through glass. You are being showered with neutrinos in your sleep. You have been your whole life, and they leave no trace. They pass through everything, caring nothing for matter, barely acknowledging it exists. Detecting neutrinos requires extraordinary effort. Physicists have built enormous tanks of water or other fluids, deep underground, shielded from all other radiation, waiting for the extremely rare moment when a neutrino interacts with a particle in the tank and produces a brief flash of light. The tanks are vast, some holding tens of thousands of tons of water, and on a typical day, only a handful of interactions occur. A handful out of the countless billions of neutrinos passing through every second. To catch a ghost, you build a room, the size of a cathedral, fill it with water, line it with photomultiplier tubes, and wait, and wait, and wait. The strong nuclear force holds quarks together inside protons and neutrons. But there is also a residual effect that reaches slightly beyond the proton and holds protons and neutrons together inside the nucleus. This is what overcomes the electromagnetic repulsion between positively charged protons crowded together in a tiny space. The nucleus of an atom is a quiet but intense battlefield. The electromagnetic force pushing protons apart, the strong force holding them together, the whole arrangement in a delicate and ancient balance. Most atomic nuclei are stable. They last forever, or close enough to forever, that the difference does not matter on any human timescale. But some nuclei are unstable. They decay, emitting particles or energy, transforming into other elements, seeking a more stable configuration. This is radioactivity, and it is a quantum process, fundamentally, irreducibly random. You cannot predict when a particular radioactive atom will decay. You can only say what fraction of a large collection will have decayed after a given time. Each individual decay is a quantum event, uncaused, unknowable in advance, happening in its own quiet time. The half-life of a radioactive element is the time it takes for half of a sample to decay. Some elements have half-lives of tiny fractions of a second. Others stretch across billions of years, longer than the Earth has existed, longer than the Sun has burned. Uranium-238, a common form of uranium, has a half-life of roughly 4.5 billion years. The Earth is about 4.5 billion years old, so roughly half of all the uranium-238 that was present when the Earth formed is still here today. The other half has slowly, atom by atom, over billions of years, decayed into other elements through a long chain of transformations, ending at lead. The decay of radioactive elements inside the Earth generates heat, and this heat is part of what keeps the Earth's interior molten, what drives plate tectonics, what shapes mountains and opens rifts and breathes volcanoes. The warmth inside the Earth is partly the slow release of quantum events, happening one at a time over billions of years. The weak nuclear force is responsible for a type of radioactive decay called beta decay, in which a neutron inside a nucleus transforms into a proton, emitting an electron and an antineutrino. The weak force is what makes the Sun burn in its particular way. It is what allows protons to be converted into other particles in the fusion chain that drives the Sun's energy. Without the weak force, the Sun would not shine. Without the weak force, the heavy elements, the carbon, the oxygen, the iron that were cooked inside ancient stars and scattered into space when those stars exploded, would never have formed. The atoms in your bones were forged in stellar furnaces that required the weak nuclear force to work as they did. You are here because of a subtle quantum interaction between particles inside long-dead stars. Let us turn now toward the quantum world's relationship with time. At the quantum level, the fundamental equations of physics are time-symmetric. They work equally well going forward or backward. There is no preferred direction. A quantum interaction running in reverse is equally valid, equally allowed. And yet, we experience time as flowing in one direction, from past to future, never the reverse. A broken cup does not reassemble. Smoke does not unrise from a fire. Where does this arrow of time come from, if not from the quantum laws? The answer, most physicists believe, has to do with entropy, the tendency of systems to move from ordered states to disordered ones, not because disorder is forced, but because there are vastly more disordered arrangements than ordered ones. The arrow of time is a statistical arrow, not a quantum arrow. The deep laws permit time to flow either way. It is the vastness of the possible that makes it flow in one. There is a strange consequence of this. The very early universe, in the first fraction of a second after the beginning, was in a state of extraordinary order, low entropy, almost impossibly organized. And since then, entropy has been increasing. The universe has been spreading out, cooling, growing more disordered. The arrow of time points in the direction of increasing entropy. Everything we call the future is the direction of growing disorder. The clocks tick, the stars age, the warmth disperses. All of this is the universe moving from its improbably ordered beginning toward the vast, tepid, disordered state it will eventually reach. And all the beauty along the way, the galaxies, the storms, the rivers, the living things, are what happens in the meantime. The quantum world and gravity do not get along well. This is one of the great unresolved problems in physics. Quantum field theory describes 3 of the 4 fundamental forces beautifully: electromagnetism, the strong force, the weak force. But it cannot accommodate gravity. Gravity, described by Einstein's general theory of relativity, is a theory of curved spacetime, of smooth geometry, of fields that vary continuously. Quantum theory is about discreteness, probability, jumps. The 2 frameworks, each extraordinarily successful in its own domain, cannot both be right when pushed to their limits. At extreme scales, the smallest possible length, the highest possible energy. Both theories are needed simultaneously, and they produce nonsensical answers. Reconciling them, finding a theory of quantum gravity, is perhaps the deepest unsolved question in fundamental physics. One candidate is string theory. In string theory, the fundamental entities are not point-like particles, but tiny, one-dimensional objects, strings, vibrating. Different modes of vibration correspond to different particles. An electron is a string vibrating one way. A photon is a string vibrating another way. And gravity, the graviton, the hypothetical quantum of the gravitational field, emerges naturally from string theory's mathematics. This is why many physicists find string theory appealing, even though it has not yet made testable predictions that have been confirmed. It includes gravity without being told to. It absorbs it as a consequence. String theory requires extra dimensions of space, beyond the 3 we experience, curled up so tightly, at every point in space, that they are far too small to detect. The universe, if string theory is correct, has many more dimensions than the ones you navigate each day. Another approach to quantum gravity is called loop quantum gravity. It suggests that space-time itself is not continuous, not a smooth fabric, but is itself quantized, made of discrete, minimum units. There would be a smallest possible length and a smallest possible time, below which the concepts of length and time become meaningless. Space would be a kind of fine mesh, a weave of quanta, each one the tiniest possible region. Between the nodes of this mesh, there is no space. Space is the mesh. This is deeply strange to try to imagine, and perhaps that is appropriate. The universe at its deepest level was never required to be imaginable. Let us rest here for a moment and think about what the quantum world might be telling us about the nature of reality. Physicists have been arguing about this since the 1920s. The view most commonly taught, known as the Copenhagen interpretation, says, essentially, that quantum mechanics describes the probabilities of what we will observe, and that asking what is really there, beyond observation, is not a meaningful scientific question. Shut up and calculate, as a famous physicist once put it. The math works. Use it. But many scientists and philosophers find this unsatisfying. Surely the world is doing something, even when no one is looking. An alternative is the many worlds interpretation, first proposed in the 1950s. In this view, the wave function never collapses. Every time a quantum measurement is made, all possible outcomes occur. In different branches of the wave function, different versions of reality, each as real as the others. When you flip a quantum coin, there is a version of you who sees heads, and a version who sees tails, and both versions continue on, real, alive, experiencing their own futures. The universe branches, constantly, silently, at every quantum event, into an unimaginable number of parallel futures, each one complete and continuous. You are here, breathing, in one branch. Other branches contain other versions of this moment, unreachable, silent, equally present. There is also the pilot wave interpretation, proposed by Louis de Broglie, and later developed by David Bohm. In this view, particles are real, definite things, with actual positions at all times. But they are guided by a wave, a real, physical wave spreading through space, that shapes where they are likely to be found. The randomness is not fundamental in this view. It comes from our ignorance of the exact initial conditions. The universe is deterministic again, if you know everything, but you never can. Each interpretation makes the same predictions as all the others. There is, as yet, no experiment that can choose between them. The quantum world keeps its philosophy, as hidden as its particles. Quantum biology is a young and quietly growing field that looks at the places where quantum effects seem to matter in living systems. We have already seen that quantum tunneling plays a role in enzyme reactions, but there are other, more surprising examples. Photosynthesis, the process by which plants and other organisms convert sunlight into chemical energy, appears to involve quantum coherence. When light strikes the antenna molecules of a plant, the energy does not simply hop from molecule to molecule until it reaches the reaction center. Instead, it seems to explore many paths simultaneously, wave-like, finding the most efficient route through a kind of quantum spreading. Photosynthesis may be so extraordinarily efficient, partly because it uses quantum superposition to search all possible paths at once. The leaf that catches the light on a quiet afternoon may be doing something more quantum than we imagined. There is also evidence that certain birds use quantum mechanics to navigate. European robins, and possibly other migratory birds, appear to sense the Earth's magnetic field using a quantum process in a protein in their eyes. The protein, called cryptochrome, can produce pairs of entangled electrons, and the way these electrons interact with the magnetic field affects the chemical reactions that follow. This gives the bird a quantum compass, a sense of the magnetic field's direction built into its vision. A robin flying south in the autumn may be reading the Earth's field through the quantum mechanics of entangled electrons in the cells of its eyes. The migratory flight of a small bird, guided by the deep strangeness of the quantum world. DNA, the molecule that holds the instructions for life, is also touched by the quantum. The mutations that drive evolution, the changes in the genetic code that allow new traits to appear and be tested by selection, may sometimes be initiated by quantum tunneling. A hydrogen atom bonded in DNA can tunnel from one position to another, changing the base pairing and introducing a mutation. The origin of genetic variation, the raw material of evolution, may have a quantum root. The fact that you exist, with your particular face and voice, and the exact weight of your thoughts, may trace back through a very long chain of cause and effect to quantum events in the DNA of your ancestors. You are, in part, a quantum outcome. The sense of smell may also have a quantum contribution. The classical theory of smell says that molecules are detected by their shape. They fit into receptor proteins, like a key into a lock. But there is an alternative theory that has been gathering some support, that the nose detects the vibrational frequencies of molecules, the way they oscillate, which is a quantum property, through a tunneling process. If this is correct, what you smell when you breathe in a rose is not just the shape of the molecule, but its quantum vibration. Its smell is a kind of music, played at the quantum scale, heard by the cells of your nose. Let us think for a moment about something called decoherence. Quantum effects, superpositions, entanglement, interference are fragile. They require the quantum system to be isolated from its environment. The moment a quantum system interacts with its surroundings, absorbs or emits a photon, bumps into a molecule, feels the heat of its surroundings, it becomes entangled with the environment. And as it does, the quantum interference fades. The superposition dissolves. The particle effectively becomes classical, definite, located, ordinary. This process is called decoherence. It is extremely fast. At room temperature, for a particle interacting with its environment, decoherence happens in an almost unimaginably short time, far faster than any process you could observe. This is why the quantum world seems hidden from us. It is not that quantum effects don't apply to large things. It is that large things interact so constantly with their surroundings that their quantum nature is instantly erased. The quantum is always there. It is just very, very shy. Building a quantum computer means fighting decoherence. You must keep your quantum bits, your qubits, isolated from the environment, long enough to perform your computation. This requires cooling them to temperatures close to absolute zero, colder than the average temperature of outer space, and shielding them from vibration, from electromagnetic noise, from any interaction at all that might collapse their delicate quantum states. The inside of a quantum computer is one of the coldest and most isolated places ever created on Earth. A small region of almost perfect stillness where quantum superpositions are allowed to bloom for just long enough to be useful. It is, in its way, a very delicate thing, a tiny corner of the universe, where the quantum world is invited to stay a little longer. Superconductivity is another quantum phenomenon that has found its way into the world. When certain materials are cooled below a critical temperature, they lose all electrical resistance, completely, entirely, not just reduced. Electrons pair up into what are called Cooper pairs, and these pairs move through the material. As a single quantum fluid, all the pairs in the same quantum state, flowing without any friction, without any loss. This is a macroscopic quantum effect, the quantum behavior of many electrons, acting in concert, visible at a scale you could hold in your hand. Superconductors are used in MRI machines to generate the powerful magnetic fields needed for imaging. They are used in particle accelerators. They may one day be used in power transmission lines that carry electricity across countries without losing any energy to heat. The quantum world, coaxed out of hiding by cold, doing useful work in the everyday world above. Lasers are also quantum devices. The word laser stands for light amplification by stimulated emission of radiation, a phrase that is cumbersome, but describes something quite beautiful. In a laser, electrons in atoms are excited to a higher energy level. When one of them spontaneously drops back to the lower level, it emits a photon. This photon then passes by another excited electron and stimulates it to also emit a photon, identical to the first in every way. Same frequency, same direction, same phase. These two photons stimulate two more, and so on. A cascade of identical photons, all marching together, in perfect quantum lockstep, emerges as a narrow, coherent beam of light. The laser in your CD player, the laser that corrects vision, the laser that reads barcodes, the laser that transmits the internet through fiber optic cables, all of them are powered by the quantum mechanics of electrons jumping between energy levels. Every time you press a button on your phone, quantum mechanics is at work. The transistors that make up computer chips are tiny switches that control the flow of electrons. They work because of a phenomenon called quantum tunneling, and because of the quantum mechanical properties of semiconducting materials, materials that conduct electricity only under certain conditions. The quantum energy levels of electrons in these materials can be shifted by applying voltage, turning the flow of current on or off. Billions of these switches packed into a chip smaller than a fingernail, switching billions of times per second, are what gives your phone its intelligence. All of modern electronics, every screen, every circuit, every chip, is the quantum world, engineered and tamed and put to work. Let us turn now towards something enormous and see how the quantum connects to the very largest things. The large-scale structure of the universe, the way galaxies are distributed, clustered in enormous filaments and sheets and voids, traces back to quantum fluctuations in the very first moments of existence. In the very early universe, the density was nearly uniform, nearly perfectly smooth. But quantum uncertainty meant that there were tiny, random density fluctuations, regions very slightly denser or less dense than average. Over hundreds of millions of years, gravity amplified these tiny variations. Denser regions attracted more matter. Matter clustered. Clusters merged. Galaxies formed. And the vast, cosmic web of galaxies and voids that fills the observable universe today is the echo and amplification of quantum fluctuations that occurred in the first tiny fraction of the universe's first second. The large-scale map of the cosmos is written in quantum ink. The cosmic microwave background is the faint afterglow of the early hot universe, a bath of microwave radiation that fills all of space, in every direction. It was released about 380,000 years after the beginning, when the universe cooled enough for electrons to combine with protons and form neutral hydrogen atoms. For the first time, before that moment, the universe was opaque, a dense, hot, glowing plasma through which light could not travel. Afterwards, suddenly, it cleared. The universe became transparent, and that first light, stretched and cooled by billions of years of expansion, is the cosmic microwave background. It reaches your skin right now, gentle and imperceptible, a whisper of the early universe, still arriving after nearly 14 billion years. The tiny variations in the cosmic microwave background, the hot and cold spots, the subtle texture, are the quantum fluctuations of the early universe, grown enormous. They are the seeds of every galaxy, every star, every planet, every life form that has ever existed. When astronomers map the cosmic microwave background, they are seeing the quantum origins of everything. The sky at night, vast and quiet, holds within it the fingerprint of the quantum world's earliest moments. Inflation, the theory that the universe underwent a period of extraordinarily rapid expansion in its first tiny fraction of a second, also has quantum roots. The energy that drove inflation is thought to have been a quantum field, and the end of inflation, when the energy decayed and the universe settled into its current, slower expansion, may have been a quantum event. Even the beginning, the very first moments of cosmic time, when the universe was smaller than anything we can easily imagine, was shaped by quantum uncertainty. The universe was born small enough that quantum effects were not marginal. They were everything. The quantum world did not emerge inside the universe. In some sense, the quantum world is the universe, stretching outward from its first infinitesimal moment to the vast and cooling now. Black holes are where the quantum and gravity most urgently demand to be reconciled. A black hole is a region where gravity is so intense that nothing, not even light, can escape. Classical general relativity says that whatever falls into a black hole is simply gone, its information lost forever. But quantum mechanics says that information cannot be destroyed. It can be scrambled, hidden, distributed, but not erased. These two requirements seem to contradict each other. This is called the black hole information paradox, and it has occupied some of the best minds in physics for decades. A physicist named Stephen Hawking showed that quantum effects near the event horizon of a black hole, the point of no return, cause it to slowly radiate energy. Black holes slowly evaporate, emitting what is called Hawking radiation, and over an almost unimaginably long time, they shrink and eventually vanish. But whether the information they swallowed is carried away in this radiation, subtly encoded, or whether it is truly lost, remains one of the deepest open questions in all of physics. Hawking radiation is so faint that no black hole we know of has been observed emitting it. A stellar mass black hole would emit Hawking radiation at a temperature so far below the cosmic microwave background that the radiation from the early universe, arriving from every direction, is billions of times more intense. To see a black hole glow with Hawking radiation, you would need the universe to have cooled far, far beyond its current temperature. It will, eventually, in an incomprehensibly distant future, when everything else has faded, black holes will glow faintly in an otherwise dark and cold cosmos, slowly releasing what they consumed, until at last, they too are gone. The Planck length is the smallest meaningful length. It is derived from the three fundamental constants of quantum gravity: the speed of light, Planck's constant, and Newton's gravitational constant, combined in the only way that produces a length. It is roughly 1.6 times 10 to the power of negative 35 meters. Writing it as a decimal would give you a 0, then a decimal point, then 34 more zeros, then a 1.6. At this scale, the smooth fabric of space-time is thought to break down. Below the Planck length, the concepts of distance and location may become meaningless. Space itself may cease to exist in any recognizable form. The Planck time, the time it takes light to travel the Planck length, is about 5 times 10 to the power of negative 44 seconds. This is the smallest meaningful unit of time. Before the Planck time, after the Big Bang, we have no theory that works. The universe is, below that threshold, unknown. The quantum world imposes a kind of granularity on everything. Energy comes in quanta. Angular momentum comes in quanta. Charge comes in quanta. Electric charge is always a multiple of the electron's charge. You cannot have half an electron's worth of charge. You cannot have 1/3. Even quarks, which carry fractional charges, always combine into groups, whose total charge is a whole number multiple. Nature seems to have decided, quietly, that certain things come only in whole numbers. There are no half steps, no gradients, no smooth continua. The world, at its foundation, is counting. The hydrogen atom is the simplest atom. One proton, one electron. And yet, even in its simplicity, it is extraordinary. The electron in a hydrogen atom can exist in different energy levels, quantum states, each with a precisely defined energy. When the electron drops from a higher level to a lower one, it emits a photon with exactly the energy of that transition. And these energies correspond to light of specific wavelengths. Each element has its own unique set of spectral lines, its own quantum fingerprint, determined by its electron structure. When astronomers look at the light from distant stars, they can identify these fingerprints and know what the star is made of without going anywhere near it. Hydrogen's spectral lines are the same, whether the hydrogen is here on Earth or in a galaxy a billion light-years away. The quantum world is universal. Its rules apply everywhere, always, without exception. There is something quietly moving about this. The same quantum laws that govern the electrons in your body govern the electrons in the most distant star we can see. The universe is, in this sense, profoundly unified. It plays by the same rules in every corner. When you look at a star, you are seeing the same quantum physics that makes you possible, the same allowed transitions, the same permitted energies, the same precise fingerprints. The universe speaks one language to every atom within it, and every atom listens. The photoelectric effect was the phenomenon that won Einstein his Nobel Prize. Not relativity, as many people assume, but the photoelectric effect. When light shines on a metal surface, electrons can be knocked loose. This was known, but what was puzzling was that the energy of the ejected electrons did not depend on the brightness of the light. It depended on its frequency, its color. Bright, dim, red light ejected fewer electrons, but at a fixed energy. Faint blue light ejected fewer but more energetic electrons. Einstein explained this by proposing that light comes in quanta, photons, and that each photon carries energy proportional to its frequency. A photon of blue light carries more energy than a photon of red light. Brightness just means more photons, each still carrying the same amount. This was one of the founding moments of quantum theory, and it was built not from abstraction, but from a very practical observation: why light knocks electrons out of metals in the particular way it does. Solar panels work because of the photoelectric effect. When sunlight strikes a semiconductor material, photons knock electrons loose, and those electrons are directed into a current. sunlight is converted to electricity through a quantum process. Every solar panel on every rooftop is demonstrating the photoelectric effect that Einstein described in 1905. The clean energy of the future is built on quantum mechanics, discovered more than a century ago. Light arrives, photon by photon, knocking electron by electron, generating the current that powers homes and cities and quiet lives. The concept of zero-point energy is another consequence of the uncertainty principle. Even at absolute zero, the coldest temperature possible, where all thermal motion has ceased, quantum systems cannot be perfectly still. To be perfectly still would mean having a perfectly known position and a perfectly known momentum, both zero simultaneously. But the uncertainty principle forbids this. So even at absolute zero, particles still jitter. They have a residual, irreducible energy, zero-point energy. You cannot remove it. You cannot cool something past it. The ground state of the universe is not perfectly still. It hums, very faintly, forever. Even stillness, at the quantum level, is not entirely still. Superfluidity is a phenomenon related to superconductivity, but occurring in fluids rather than solids. Certain substances, most famously liquid helium-4, when cooled to very low temperatures, enter a superfluid state, where they flow without any viscosity at all. They cannot be made to stand still inside a rotating container. They creep up the walls and over the lip and out. They flow through the tiniest possible cracks and openings. They have no friction, no resistance. This happens because the helium atoms, cooled sufficiently, all drop into the same lowest quantum state, becoming, in a sense, one quantum thing rather than many separate atoms. A macroscopic quantity of helium behaving as a single quantum entity. The quantum world made visible to the eye. The Bose-Einstein condensate is another extreme version of this phenomenon. It was predicted by Satyendra Nath Bose and Albert Einstein in the 1920s and first created in a laboratory in 1995. When certain types of atoms, called bosons, as opposed to fermions, are cooled to temperatures just barely above absolute zero, they all collapse into the same quantum state, forming what is essentially one giant quantum object. Hundreds of thousands of atoms, behaving as a single entity, all described by one wave function. In a Bose-Einstein condensate, you can see quantum effects that normally exist only at the atomic scale, playing out at a scale visible to the naked eye. It is, in a very real sense, the quantum world reaching up to meet us. Let us pause here for a moment of soft reflection. You are lying still, and in the atoms of your body, in the electrons surrounding each nucleus, in the quarks and gluons inside each proton and neutron. The quantum world is in full and constant motion. Uncertainty is your constant companion. Superposition hums beneath your every breath. Tunneling happens in your enzymes, with every heartbeat. You are not a thing that exists in the quantum world. You are the quantum world expressing itself at a scale large enough to wonder about it. The astonishment goes both ways. The universe, in its quantum form, has produced beings capable of discovering it, and then wondering, quietly, in the dark, what it means. The double-slit experiment, which we touched on earlier, has been called the most beautiful experiment in physics. It has also been performed with things larger than photons and electrons. It has been performed with atoms, with molecules. With molecules made of 60 carbon atoms, Buckminster fullerene, known as buckyballs, each one large enough to be seen in an electron microscope. These molecules, each containing 60 atoms, showed interference when passed through a double slit. Each one passed through both slits simultaneously, as a wave of probability, and interfered with itself. The quantum world extends if you cool things carefully enough and isolate them sufficiently to objects you can see under a microscope. The boundary between quantum and classical is not a sharp line. It is a gradient, and we are gradually pushing further into the quantum side of it. The quantum eraser experiment is one of the most quietly mind-bending of all quantum experiments. It is a variation on the double-slit experiment, in which a detector is used to mark which path a photon takes through the slits. When the path information is available, the interference pattern disappears. But then, in the quantum eraser, a later measurement is made that erases the path information, destroys it, makes it impossible to retrieve, and the interference pattern returns. The information about which path was taken is what matters, not what the detector physically did. If the information could in principle be retrieved, no interference. If it is irrecoverably erased, interference returns. The universe seems to track, at the quantum level, what information exists and shapes its behavior accordingly. There is even a delayed choice version of this experiment, in which the decision to erase the path information, or preserve it, is made after the photon has already passed through the slits. And yet, the outcome, whether there is interference or not, reflects the later decision. The present, in some subtle quantum sense, seems to reach back and shape the past. Not in any way that allows signaling, not in any way that contradicts causality, but in a way that makes the word before and the word after a little softer at the edges than they seemed. The quantum Zeno effect is another strange visitor from the quantum world. If you observe an unstable quantum system very frequently, very rapidly checking whether it has decayed, you can slow its decay. In fact, in the extreme case of continuous observation, you can prevent it from decaying altogether. Watching something in the quantum world can stop it from changing. The name comes from Zeno's paradoxes of motion, the ancient Greek philosopher's argument that an arrow in flight, at each instant, is motionless and therefore cannot move. The quantum Zeno effect is, in a strange way, the universe making that paradox real. for a moment, very briefly, at the quantum scale. The ancient puzzle and the modern equation, reaching across millennia to touch each other quietly. Quantum cryptography uses the fundamental properties of quantum mechanics to create communication channels that are theoretically unbreakable. The key idea is simple and elegant. If you send a quantum key, a sequence of quantum states, between two parties, any eavesdropper who tries to intercept it must measure the quantum states to read them. But measuring a quantum system disturbs it. The eavesdropper leaves fingerprints, disturbances that can be detected. If the key arrives undisturbed, you know no one intercepted it. If it is disturbed, you know someone tried. Security guaranteed not by clever mathematics, but by the laws of physics, by the fact that you cannot look without leaving a mark. Quantum cryptography has been demonstrated over long distances, including through fiber optic cables and between ground stations and satellites. The quantum world is becoming, slowly and quietly, an infrastructure. The idea of quantum teleportation sounds like science fiction, but is a real and demonstrated phenomenon. It does not mean transporting matter from one place to another. It means transferring the quantum state of one particle, all the information needed to describe it, to another particle in a different location, using entanglement and a classical communication channel. The original particle is destroyed in the process. The distant particle becomes the original. Not the same matter, but the same quantum information, the same state, perfectly transferred. It has been achieved with photons, with ions, over increasing distances. The quantum state of a particle, teleported across a room, across a city. The quantum world, it turns out, does not require matter to travel. In order for information to travel, there is a beautiful symmetry at the heart of quantum theory, called CPT symmetry. It states that if you take any physical process and simultaneously reverse the charge of every particle, reflect everything in a mirror, and run time backward, you get an equally valid physical process. The universe looks the same under this combined transformation. This is one of the most fundamental symmetries known. It has never been observed to be violated. Individual symmetries, charge reversal alone, mirror reflection alone, can be and are violated in certain processes. But the combination of all three seems inviolable. The universe, in this mirror, is its own reflection. The search for symmetry has been one of the driving forces of 20th and 21st century physics. Many of the deepest discoveries have come not from measuring things directly, but from asking, what symmetries does the world obey? Noether's theorem, a result proved by the mathematician M.E. Noether, in 1915, shows that every continuous symmetry in nature corresponds to a conservation law. The symmetry of time, the fact that the laws of physics are the same today as yesterday, gives rise to conservation of energy. The symmetry of space, the fact that the laws are the same here as there, gives rise to conservation of momentum. the symmetry of orientation. The fact that no direction in space is special gives rise to conservation of angular momentum. Every constant of nature, every conserved quantity, is the shadow of a symmetry. The world is built on a kind of deep, quiet harmony. The measurement problem in quantum mechanics is one of the most honestly unsettled questions in all of science. It asks, what exactly happens when we measure a quantum system? Why does the wave function appear to collapse? What triggers it? The Schrödinger equation, the fundamental equation of quantum mechanics, evolves a wave function smoothly and continuously, always, without any collapse. And yet, when we measure, we always get a definite result. The two seem incompatible. Something must bridge them. But what? This is the measurement problem. And after nearly a century of quantum mechanics, physicists still do not agree on the answer. The most fundamental physical theory we have rests at its interpretive core on an open question. There is something, I think, almost beautiful about that. The best theory we have is honestly and openly unfinished. It admits what it does not know. It does not pretend to completeness. Science, at its best, is not a set of answers, but a discipline of honest questions. And the quantum world is the place where the questions are largest and most persistent, and most honestly carried. The researchers who spend their lives on these problems, who sit with equations and paradoxes, and thought experiments, and the careful, patient work of running experiments, are not trying to find final answers. They are trying to push the question a little further, a little deeper, into the unknown. Let us think now about the quantum nature of color in a new way. You see the world in color because the cells in your retina, the cone cells, each contain photopigments that absorb photons in different frequency ranges. The photopigment in a cone cell absorbs a photon and changes shape. A quantum event, a single photon absorbed by a single molecule. This shape change triggers a biochemical cascade that eventually produces an electrical signal that travels to your brain. The experience of seeing red, the warm, deep, full sensation of redness, begins with a single photon hitting a single molecule in a single cell in your eye and changing its quantum state. Everything you have ever seen started as a quantum event. The face of someone you love, the color of the sky, the soft glow of the lamp beside you. All of it, photon by photon, quantum jump by quantum jump. Hearing, too, reaches the quantum at its limit. Sound is pressure waves in air, classical, mechanical. But in your ear, in the hair cells of the cochlea, the transduction of mechanical vibration into an electrical signal involves ion channels that open and close in response to mechanical force. And at the very edge of hearing, the quietest sound you can detect, the displacement of the sensory hair cells, is smaller than the diameter of a hydrogen atom. The ear at its most sensitive, is responding to displacements. At the quantum scale, the softest sound you have ever heard, a whisper, a rustle, the sound of breathing in the dark, was detected by your ear through processes operating at the border of the quantum world. The quantum world and the sense of touch have a beautiful and simple relationship. When you press your hand against a surface, you feel resistance. But your hand does not actually touch the surface in the way we often imagine. The atoms of your hand never contact the atoms of the surface. What you feel is electromagnetic repulsion, the electron clouds of your hand's atoms, pushing against the electron clouds of the surface's atoms. The Pauli exclusion principle preventing them from occupying the same space. Touch is quantum electrodynamics. You have never, in your entire life, physically touched anything. You have only ever felt the quantum breath of electrons repelling each other across a void. This is not a diminishment. The feeling is real. The warmth is real. The pressure of a hand held is real. But what it is made of, the mechanism behind the sensation, is extraordinary and strange and worth carrying with you, even softly, even half remembered in the morning. That the world, at every point of contact, is held apart by quantum forces. That the sensation of solidity is, beneath itself, mostly empty space, humming with quantum law. Let us now drift toward the question of consciousness, not to resolve it, because no one can, but to notice where it touches the quantum world. Some physicists and philosophers have suggested that quantum mechanics might play a role in consciousness, that the uncertainty and superposition of the quantum world might be part of why consciousness is so hard to explain in purely mechanical terms. This view, associated with, among others, the physicist Roger Penrose, is not mainstream, and most neuroscientists are skeptical. The brain is warm, wet, and noisy, conditions under which quantum decoherence normally destroys very quickly. But the question has not been fully closed. The connection between observation and physics, between measurement and meaning, touches something that has not yet been cleanly resolved. What it means to observe in a universe where observation changes things. This question floats, unanswered, at the edge of both physics and philosophy. There is a version of the quantum world story that is just about numbers, equations and measurements and predictions. And then there is the version we have been tracing tonight, which is about what those numbers might mean, about what kind of universe could possibly work this way, about what it tells us, that reality, at its most fundamental, is not fixed, not determined, not already written, but genuinely, deeply, irreducibly open. The universe, at its smallest scale, is not a machine. It is something stranger, something less like clockwork, and more like weather. Governed by laws, yes, but full of uncertainty, full of probability, full of outcomes that are not chosen until the last possible moment. The quantum world has been explored for about a century now. In that time, it has given us lasers and transistors and MRI machines, and superconductors and nuclear energy, and the beginning of quantum computing. It has overturned our understanding of what the world is made of and how it behaves. It has shown us that our intuitions about reality, about objects having definite positions, about causality, about the independence of distant things, are approximations, useful at large scales, but not fundamental. The true nature of the world is weirder than anything our ancestors imagined. And it is also more beautiful, more intricate, more surprising. And we are still only at the beginning of understanding it. Some of the greatest experiments still to be done involve probing the boundary between the quantum and the classical, finding out exactly where the quantum strangeness fades into ordinary behavior, and why. Others involve testing quantum mechanics to even higher precision, seeing if, at some extreme, it finally breaks down and points towards something deeper. Others are looking for quantum gravity, for the theory that will unite the quantum world with space-time, the small with the large, the uncertain with the curved. And some are simply trying to understand what quantum mechanics means, which interpretation is right, what the wave function really is, whether there are many worlds or only one. The quantum world, a century in, is still mostly frontier. You are part of this frontier, in a way. Not because you are a physicist, but because you are made of quantum things, because the electrons in your neurons are subject to the uncertainty principle, because the photons entering your eyes right now, even in the dark, even the faint thermal photons, are following the rules of quantum field theory. Because the atoms of your body were forged in quantum furnaces and scattered across space by quantum events and gathered here over billions of years into you. You are not separate from the quantum world. You are its most complex expression that we know of. A quantum system, large enough and organized enough to wonder about itself. The electron has been known since 1897. For more than a century, humans have been studying the simplest quantum particle, and still, every decade brings new surprises, new measurements that refine our understanding. The electron's magnetic moment has been measured to extraordinary precision, more than a dozen significant figures. And the predicted value from quantum electrodynamics matches it to that same extraordinary precision. This is the most precisely tested prediction in the history of science. A number calculated from first principles, matching a measured value to more than 12 decimal places. There is something quietly humbling about this. The equations that came from human minds match the numbers the universe produces with a precision that suggests we have found something real, something that goes beyond clever guessing and into genuine understanding. And yet, the same framework that achieves this extraordinary precision cannot tell us what the wave function really is, cannot tell us why measurement collapses it, cannot be reconciled with gravity, cannot tell us why the universe is made of matter and not nothing. The most successful theory in physics is, in the deepest sense, still deeply puzzling. This is not a failure. This is science being honest. This is a discipline that has the integrity to say, we can predict it perfectly, and we do not fully understand it. The humility of that is, I think, one of the most admirable things that human knowledge has produced. Let us rest now in the image of the quantum field, that invisible ocean that fills all of space. Right now, as you lie still, you are immersed in these fields: the electron field, the photon field, the Higgs field, the quark fields. They pass through you, and through the walls around you, and through the earth below you. They extend to the edge of the observable universe, and, presumably, further. You are not separate from these fields. The particles that make you up are excitations of these fields, little ripples in the fabric. You are a temporary, organized, self-aware disturbance in the quantum fields of the universe. And when this disturbance eventually settles, as all disturbances do, over time, the fields will still be there, still spreading, still humming, still, in their quiet way, vibrating with possibility. The universe began as a quantum event. This is perhaps the most quietly strange idea of all, that the beginning itself, the very first moment, was subject to quantum uncertainty. Some physicists have proposed that the universe arose as a quantum fluctuation of nothing, that even the void is unstable in the quantum sense, and that from a perfect nothingness, a universe could emerge through a process analogous to the virtual particles that pop in and out of the vacuum. The universe as a quantum fluctuation that happened to last long enough to produce stars and planets and eyes and minds. It is, at minimum, a thought worth holding gently, in the dark. Not everyone accepts this picture. The question of why there is something rather than nothing has no agreed scientific answer. Saying, the universe is a quantum fluctuation, raises the question of what quantum laws governed before the universe began, and what before even means, when there was no time. These are honest, hard questions. Physics can bring them into sharper focus. It cannot yet answer them. Perhaps it never will. Some questions may live permanently at the edge of what science can reach, not because science is limited, but because the questions themselves live beyond the boundary of the observable. And there is a certain peace in that, too, a certain relief in knowing that not everything has an answer, and that this does not mean the asking was wasted. The quantum world is, at its heart, a world of relationship. Particles become definite through interaction. States are defined by what they are measured relative to. Entanglement is a form of relationship, so deep it has no classical analog. Even the forces, electromagnetism, the strong force, the weak force, are understood as the exchange of particles between other particles, a constant quantum conversation. The universe, at its most fundamental, is not a collection of objects. It is a web of interactions, a network of relationships, everything connected to everything else, through the exchange of quanta. Nothing exists in isolation. Nothing is entirely separate. Everything that is partly defined by everything it has ever interacted with. You carry, in the atoms of your body, a record of interactions, stretching back to the beginning. The carbon in you was forged in a star that has been gone for billions of years. The iron in your blood was born in the death throes of a massive star that collapsed and exploded long before the sun existed. The hydrogen in the water of your cells is as old as the universe, formed in the first few minutes, after the beginning, when the universe was hot enough to fuse protons into nuclei. You are, in the most literal sense, ancient. Your atoms have been part of the universe since near its very beginning. The quantum events that shaped them, the nuclear reactions, the decay chains, the random fluctuations, happened billions of years ago, and their consequences. Are you breathing in the dark now? Quantum mechanics has, over the course of its history, been tested in more ways than almost any other scientific theory. And every single test, without exception, has confirmed its predictions. This is remarkable. No experiment, anywhere, in nearly a century of trying, has found a place where quantum mechanics breaks down. At every scale where it applies, in every regime where it has been tested, it holds. We have no theory in physics, more tested or more confirmed. And yet, because its implications are so strange, because it demands so much revision of our intuitions, we have still not entirely made peace with it. We use it. We rely on it. We build technology from it. And we still argue about what it means. Perhaps that is the right response. Perhaps meaning, for something this deep, takes longer than a century to settle. Perhaps the generations who inherit our knowledge will find a way of thinking about the quantum world that is as natural to them as our ordinary experience of objects and surfaces is to us. Perhaps the strangeness will one day feel less like a violation of common sense and more like an expansion of it. As quantum mechanics has slowly entered the culture, through technology, through popular science, through conversations like this one, something is shifting, slowly. The quantum world is becoming a part of how we think about ourselves and our place in the universe. We are, slowly, becoming comfortable with uncertainty. And there is something in that, worth carrying into sleep. The universe, at its most fundamental, is not anxious about uncertainty. It does not worry about which outcome will occur. It simply holds all possibilities open, with perfect equanimity, until the moment of interaction. And then whatever happens, happens, and the world continues. The quantum world has been uncertain for 14 billion years. It has never resolved its uncertainty into certainty. It has never decided to be more definite. And look what it has made. Look at the galaxies, the stars, the living planet, the quiet room where you lie. Uncertainty, held with patience, becomes everything. You do not need to understand the equations. You do not need to follow every argument. It is enough, tonight, simply to carry a sense of it. The soft and persistent strangeness of the world below the world, the quantum humming beneath every surface, the wave of possibility that underlies every solid thing. Your blanket, your pillow, the air, the walls, your own quiet body. All of it, at its foundation, is quantum. All of it is uncertain, entangled, probabilistic. All of it is, at the deepest level, a shimmer. And yet here it is, solid enough to rest in, warm enough to sleep within, real enough to hold you. The quantum world does its work, without asking for acknowledgement. Electrons tunnel through barriers, in your enzymes, whether or not you know it. Photons make quantum jumps, in the cells of your retina, whether or not you understand the mechanism. The Pauli exclusion principle holds your atoms apart, without any effort on your part. The quantum world sustains you, silently, constantly, without fanfare. It has been doing so since before you were born, since before the planet formed, since the first atoms gathered from the quantum noise of the early universe. It will continue, long after every mind that wondered about it has gone quiet. The quantum world does not need to be understood to do what it does, but it is, perhaps, a little richer for being wondered at. The Higgs field, that pervasive field we mentioned earlier, is everywhere you have ever been. It fills the room you're in right now. Every particle that has mass gets it by interacting with this field, by being slowed, in a sense, by the field as it moves through space. Mass is resistance. Inertia is interaction with the Higgs field. The reason your body has weight, the reason you do not simply pass through the Earth, like a neutrino, is this field, this pervasive quantum field, pushing back. The heaviness of sleep, the way your body feels settled and still, is, at its most fundamental, the Higgs field, holding you to yourself. The universe has 4 fundamental forces. We have touched on all of them tonight. Gravity, electromagnetism, the strong nuclear force, the weak nuclear force. They operate at different scales. They have different strengths. They are carried by different particles. Gravity is by far the weakest, astonishingly weak compared to the others, and yet it dominates the large-scale universe, because it is long-range and always attractive, and because matter is everywhere, and even the weakest force accumulates, over vast distances and vast quantities. A tiny bar magnet can lift a paperclip against the gravitational pull of the entire Earth. Electromagnetism against the gravity of a planet, and the magnet wins. And yet gravity sculpts the cosmos. The strongest force is local. The weakest force is everywhere. There is a dream of unification. that has run through physics for a century. The hope that all four forces are aspects of a single, deeper force. Already, electromagnetism and the weak nuclear force have been unified into the electroweak force. They are the same force, seen from different energies. At very high energies, energies that existed in the early universe, and that we can briefly recreate in particle accelerators, the two forces become indistinguishable. The next step, incorporating the strong force, is the goal of grand unified theories, which remain speculative. And incorporating gravity into this single picture remains the great goal, the dream of a theory of everything. Simple, unified, complete. Perhaps it will come, perhaps it will not, but the seeking is real, and the progress, slow as it sometimes is genuine. Particle accelerators, the great circular machines that smash particles together at near light speed, are the instruments of this search. The Large Hadron Collider at CERN, near Geneva in Switzerland, is the largest machine ever built by humans. A ring nearly 27 kilometers in circumference, buried deep underground. Inside it, protons are accelerated to more than 99.999% of the speed of light, and then made to collide. For a tiny fraction of a second, conditions in the collision point resemble those of the very early universe. The debris of these collisions is studied by detectors the size of buildings, looking for particles, patterns, signatures that might reveal what lies beyond the Standard Model. It was here that the Higgs boson was detected in 2012, the last missing piece of the Standard Model, found after decades of searching. The machine found something predicted 48 years earlier. The quantum world keeps its promises. Dark matter and dark energy are perhaps the two largest mysteries that hang over modern physics. Dark matter is a form of matter that does not interact electromagnetically. It neither emits nor absorbs light, but it does have mass, and therefore gravity. We know it exists because of its gravitational effects on galaxies. Galaxies rotate in ways that only make sense if there is vastly more matter present than we can see. About 85% of all the matter in the universe appears to be dark matter. Everything we can see, all the stars, all the planets, all the gas clouds, all the light, is only 15% of the matter that exists. The visible universe is the minority. The majority is dark, silent, and unknown. Dark energy is stranger still. It is a form of energy that pervades all of space and is responsible for the accelerating expansion of the universe. The universe is not just expanding, it is expanding faster and faster, pushed apart by this dark energy at every point in space. We do not know what dark energy is. One candidate is the vacuum energy, the zero-point energy of quantum fields. But when physicists calculate this, they get a number that is spectacularly wrong. The observed dark energy is smaller than the theoretical vacuum energy, by a factor that, when written out, would require a 1, followed by more than 100 zeros. This is the largest discrepancy between theory and observation in the history of science. Something, somewhere, is profoundly misunderstood. The dark energy problem may require a revision of quantum theory, of cosmology, of both, or perhaps of something we have not yet thought to question. And so, the quantum world, vast as our understanding of it has grown, still holds its deepest secrets. What is dark matter made of? What is dark energy? How does quantum mechanics become classical mechanics? As systems grow large? What happened before the Big Bang? Or does that question even make sense? Why are the constants of nature, the strength of gravity, the charge of the electron, the mass of the Higgs boson, the particular values they are? Could they have been different? Are they different? Somewhere, in other universes we cannot reach? The quantum world asks more questions than it answers, and every answer it gives leads to 3 more questions waiting behind. This is, I think, a deeply human thing. We are the universe, wondering about itself. We are the quantum fields, organized into creatures who look up and ask what they are made of. There is something quietly extraordinary about that. Not extraordinary in a loud way, not in a way that demands your attention or requires you to be awake. Just a small, gentle, persisting wonder, the kind that can live in the back of a sleeping mind and surface sometimes in the softest moments when the world is quiet and the only thing moving is your breath. The quantum world is not far away. It is not in a laboratory, or a particle accelerator, or a textbook. It is here, in this room, in this moment, in the slow rise and fall of your chest. Every breath is a quantum event, many times over. The oxygen molecules you breathe, binding to hemoglobin in your blood. Through quantum chemistry, the electrons jumping and settling, the bonds forming through quantum mechanical overlap. You are, in your breathing, a quantum process. In your sleeping, a quantum process. In your dreaming, whatever dreaming is, a quantum process. All the way down, it is quantum. All the way up, it is you. Let there be a slowness now in how you receive these words. There is no hurry. The quantum world has been doing its work for 14 billion years and will continue for far longer than we can imagine. It does not need you to be awake for it. It does not need you to understand it. It simply is. Beneath you, within you, around you. The quiet, constant, ancient hum of particles and fields doing what particles and fields do. And you, here, in this small, warm pocket of the universe, can let yourself be carried by it. You do not need to hold anything. You do not need to understand. You can simply be what you are, a temporary, beautiful, quantum arrangement of ancient atoms, and let the rest go. The scientists who first discovered these things must have felt something like vertigo. To look at the world and find, underneath it, something so completely unlike what you expected. Probability instead of certainty, waves instead of particles, entanglement instead of independence, must have been deeply disorienting. Niels Bohr, one of the architects of quantum theory, is said to have remarked that anyone who is not shocked by quantum mechanics has not understood it. There is truth in this. The quantum world is not gentle with our assumptions. It does not meet us where we are. It asks us to come to it, to revise, to expand, to let go of what we thought we knew, and stand, a little uncertain, in its presence. And perhaps that is not so different from other things that ask the same of us. There is a kind of rest available in the quantum picture of things. If nothing is fixed until observed, if uncertainty is fundamental, if even the most basic facts about particles are genuinely undecided until the moment of measurement, then there is, perhaps, a permission in that. A permission to be uncertain yourself, to not know what tomorrow will hold, to be, in this moment, in superposition, many possible futures, still open, still available, nothing collapsed yet into what must be. The quantum world does not worry about its uncertainties. It simply holds them with perfect equanimity and lets the next moment arrive when it does. You can do that too. You can let the next moment come on its own. If you have closed your eyes, that is a good thing. If you are drifting, that is exactly right. The quantum world is still there, still humming, still doing its ancient and wordless work. You do not need to watch it. You do not need to think about it anymore tonight. You can simply feel the weight of your body against whatever holds you, the soft push and pull of your breathing, the warmth of the air around you. Let the quantum world do what it does. Let it tunnel and entangle and collapse and superpose in all the places you cannot feel or see while you rest. You have been held by these forces every moment of your life. They have never failed you. They will hold you through the night. The stars above you, whether or not you can see them, are burning by quantum tunneling right now as you breathe. The electrons in the atoms of the ceiling are vibrating in their probability clouds, nowhere and everywhere within them. Even now, the vacuum is fizzing with virtual particles appearing and vanishing at every point in the space of the room. The Higgs field fills every corner. The photon field carries whatever faint light reaches you. The neutrinos continue their endless, effortless, uncaring passage through you. And through it all, you breathe. You are still. You are quiet. You are, in your stillness, a part of all of this. Let the breath come slower now. There is nothing you need to do. Nothing you need to figure out. Nothing you need to hold on to or carry forward. The quantum world will do what it does. Without your guidance, the universe will continue its patient work. while you sleep. Stars will form and age in distant galaxies. Particles will decay, and fields will ripple. And somewhere, in a cool and quiet laboratory, an electron will tunnel through a barrier it had no right to cross. And you will be here, warm, still, breathing, resting in the fabric of it all. You are made of stars. You are made of quantum fields. You are the universe, folded into a form that can lie down and rest. And tonight, that is exactly what you are doing. Resting in the world that made you, breathing the air that your atoms have breathed before, in other bodies, in other times, returning quietly to the stillness that is always underneath. Close your eyes, if they are not already closed. Let the thoughts soften at their edges. Let the quantum world hum its quiet, ancient hum beneath your every thought. You do not need to understand it. You do not need to remember it. You only need to breathe. In and out. Slow, easy, still. The quantum world is here, holding everything together in its invisible, beautiful, reliable way. And you are part of it. Always were. Always will be. Even when you sleep. Especially when you sleep. Drift now into the soft, dark, into the place where thoughts loosen and dissolve, like morning fog, lifting off a quiet lake. Let the last images drift through you. The electron in its cloud, the photon taking every path, the entangled particles, separated by the width of the universe, and still, somehow connected. These are the things the universe is made of. These are the things you are made of. Let them drift. Let them go. Let the breath come on its own, without effort, without thought. The quantum world needs nothing from you tonight. It asks only that you rest. And so you do, deeper now, softer, quieter, into the still, ancient, quantum dark